Hi everyone, and welcome to Lab 5, Choose Your Own Adventure. So in this lab, or rather, the video that I chose is the slinky video, in which you have a slinky falling from static equilibrium. And in the video, the guy holds a slinky which is dangling freely. He lets it go, and we're going to analyze what happens after it has been released. So we're going to gather our data in Tracker and then create a model for it, observing the slinky's movements. And some of the things that we are using in this lab as far as physics principles is Newton's second law, momentum principle, because we have to update the movement of the spring, and Hooke's law to show the linear relationship between the spring's movements. So in the video, the guy basically explains that there are a few different ways in which the slinky is going to react or move. That it's either going to come top to bottom, bottom to top, or they're essentially going to meet or approach each other in the middle. So from the actual slinky video, the slinky, he lets go of the slinky that's dangling freely, and the top starts to approach the bottom. And this is a good example of Hooke's law because it's following that linear motion. So in my code, I tried to make it exhibit the motion that it had in the video to the best of my ability. But as you can see in my tracker data, the first one is the top of the slinky, and you can see that it goes from, I had it adjusted to like a 1 meter stick. You can see that it goes from 1 meter all the way down to 0, and then the bottom of the slinky stays about at the same position throughout time. So in my code, I first made a reference, which is our red line cylinder, and I have that from the top of the slinky to about halfway through. My top of the slinky starts at the top of the cylinder. I have both of them at a mass of about 1, and the positions start at 0, 0, 0. So I made another helix structure to represent the slinky itself, and my change in time is about 0.1 seconds at a rate of about 20. So we find the length of the total length of our slinky, we calculate our spring force, we calculate the gravity on our top and the bottom of our slinky, which I have represented by circles or spheres, and after we find our net force, we apply that to our momentum update formulas, which is the top of our slinky plus the spring force times the change in time, the same for the bottom. After that, once we do our momentum update, then we do our position update times the change in time. And lastly, that should then update the position of the top of our spring as it approaches to the bottom of it and how that reacts to it or relates to it. So here's the video of my slinky model. So to conclude Lab 5, the question is, does the bottom of our model stay stationary just like in the video? And yes, for the most part, the slinky in the model does. As the top approaches or gets very close to the bottom of our slinky, that's when you can see the force being applied to the rest of the slinky, or at the bottom of the slinky, and that starts to move down as well. They basically create opposite forces or equal and opposite forces against each other. So you can see the force at the top being applied to or shifting through the slinky as it becomes compressed. So in conclusion, once the slinky is at equilibrium position, that's when you can start to see the acceleration downwards, or the force that's, being counteracted by the force coming down, or the force of the top of the slinky. So thank you. That is all I have for Lab 5. I hope you enjoyed it, and have a great day. Bye!